Now that we've had a look at zero divisors and units, we're going to look at two types of rings called integral domains and fields. We're first going to review the definitions of zero divisors and units. We're going to use those to help us define integral domains and fields. And then we're going to analyze two different examples. So let R be a ring. Remember that we say that A is a zero divisor if two things happen. A is non-zero, and then there's another non-zero element B, such that when you multiply A times B in either direction, A times B or B times A, you get 0. If you have a ring, a multiplicative identity is also called an identity or a unity, is an element that we call 1, where when you multiply it on either side of any element of the ring, you leave that ring alone. So A times 1 equals A, 1 times A also equals A for all elements A. If A is in R, we say that B is a multiplicative inverse of A if A times B and B times A are equal to the multiplicative identity. And then finally, we call A a unit if it has a multiplicative inverse. So integral domains and fields are very much related to both zero divisors and units. And also, they demand an extra condition that multiplication is commutative. Remember, in general, multiplication doesn't have to be commutative, but for integral domains and fields, it does. So let R be a ring. First thing I'm going to do is give you a name for rings that happen to have a commutative multiplication. They are called commutative rings. Now, so R is a commutative ring if the multiplication in R is commutative. Now that may be a little bit confusing because of course we all know that addition is commutative in all rings. So when we say commutative ring, we're adding that extra commutative. We're not saying that addition is commutative. It's automatically commutative just being a ring. The commutative is referring to multiplication because that's the only operation that may or may not be commutative. We say that R is an integral domain if it is a commutative ring, first of all, and it does not have any zero divisors. So that means multiplication has to be commutative for an integral domain, and it can't have any zero divisors. We also say that R is a field if it is a commutative ring, and also every non-zero element of R is a unit. So we've seen some where we have some non-zero elements not being a unit. A field has to have every single element having a multiplicative inverse. So let's look at our Z3 and notice that I'm getting super lazy with the notation. I'm sick of drawing those darn brackets and subscripts. I'm going to say Z3 is equal to 0, 1, and 2. And you got to remember that 0 does not mean the number 0. It means the congruence class that contains 0. So 0, 3, positive 6, negative 6, etc. And 1 and 2 similarly. All right, so, but I'm just going to write them 0, 1, and 2 because, again, sick of writing the brackets. So if we want to look at zero divisors, well, let's look at the ways that we can multiply non-zero elements together. Since we only have 3 elements altogether and only 2 of them are non-zero, that should be easy to do. If we have 1 times 1, we get 1. 1 times 2, which is also 2 times 1 is equal to 2. 2 times 2 equals 1. As you can see, multiplying non-zero elements never gives us 0. No zero divisors, which means that Z3 is an integral domain. Let's look at its units to see if it's a field. Well, notice that if we have 1 times 1 equals 1, which means that 1 is a unit. It has a multiplicative inverse itself. Also, 2 times 2 equals 1, which means that 2 is a unit. And those are the only non-zero elements. They are units. They have multiplicative inverses, which means that Z3 is also a field. So it's an integral domain and a field. But if we look at Z4, that's 0, 1, 2, and 3, right? And again, those are congruence classes, not integers, so don't get any funny ideas. If we look at zero divisors, yeah, we have one. 2 times 2 is equal to 0. That means 2 is a zero divisor. That means that Z4 is not an integral domain. Let's see if it's a field. For our units, yeah, 2 is also a troublemaker, not just because it's a zero divisor, but because it doesn't have a multiplicative inverse. No matter what we multiply 2 by, 2 times 1 equals 2, 2 times 3 equals 6, which is also 2. None of those give you 1, which would make it a unit. So that means Z4 is not a field. So now it's a good idea for you to work on the activities for integral domains and fields. That's on the PDF file included with this video.